Welcome to Lecture 4.2, Equivalence Relations and Equivalence Classes. The previous lecture was on binary relations on a set, and I strongly recommend that you watch that lecture first because I will assume the knowledge and the basic definitions that were given in it. So recall that binary relation on a set was a collection of ordered pairs, say of the form R equals maybe A, B, B, C, C, A, things like this. Although sometimes we had a special symbol because it was inconvenient to write something like A comma B for A is related to B, so sometimes we wrote things like A is equivalent to B or A is less than or equal to B. So we invented a symbol like this. And even though a binary relation was any collection of ordered pairs, there were two that were more important, that arose a lot more. One of them were equivalence relations, which are think of them as generalized equality, and the other one were partial orders, which were generalized less than or equal to. So this lecture is going to be on the first one, equivalence relations. Remember that an equivalence relation on a set A is any relation, so of this form, that is reflexive, transitive, and symmetric. So reflexive means that everything is related to itself, and then I think transitive and symmetric, you probably know what those are. We can always visualize a relation on a finite set A with a directed graph, or digraph for short. The vertex set is just the set of elements itself, and we put a directed edge from A to B if A is related to B. In other words, if the ordered pair A and B is an R. Since equivalence relations are symmetric, this digraph will always be bidirected. And that means anytime that we have an edge from A to B, we have an edge back from B to A, which we often just write as a double edge like this between A and B. So for convenience, we'll usually drop all arrow tips, so all edges are undirected, and also all self-loops. So remember that a self-loop is just a directed edge from a vertex to itself, and since equivalence relations are reflexive, every vertex will have that on it, so there's really no reason to include it. We can just remember that everything is related to itself. So in summary, for every edge between two vertices, it will appear as a bidirected edge, and every vertex has a loop, and there's really no reason to carry this extra information. So we usually just draw the graph with undirected edges, so this becomes that. Finally, I should mention that I specified a finite set A, but A does not have to be finite. If A is infinite, but it's discrete, something like a grid of, or a lattice of coordinates, then it certainly makes sense to draw a graph, part of an infinite graph, and just do something like this, dot, dot, dot. However, if our set A is like the real numbers, that's just not feasible. So that's why I said we can always do this with a finite set, and then there are certain infinite discrete sets where this works as well. Now that we have the definition of an equivalence relation, we come to the all-important definition of an equivalence class. This was not done in the previous lecture. Let's start with an equivalence relation R on a set, I'm going to call it big A, because plain old A is going to be an element in big A. So big A could be finite or infinite, it doesn't matter. Technically, the relation R is a collection of ordered pairs of the form AB, though we will usually write these with some sort of equivalence symbol, like this equal sign that has 3 lines instead of 2, or an equal sign with the squiggly line on top, or just a squiggly line, or a double squiggly line, or a single line with the squiggly line on top. Any of these are commonly used. What's not commonly used for a general equivalence relation is equality, because that is reserved for actual equality. Okay, so given that, the equivalence class containing an element A of our set, big A, in plain English, it's just the set of elements in big A that are equivalent to it. So we usually write this with brackets. So bracket A, or sometimes we'll write A with a bar on top, but I think bracket A is the most common. It is formally the set of all B in big A such that A is equivalent to B. Two different ways to write that notationally. We denote the set of equivalence classes by what looks like A slash R, or A slash the equivalence relation symbol, though we usually just say A modulo R, or A mod R, or even A mod the relation. Let's do some examples. In the first one, let big A be the set of all people. First, consider an equivalence relation defined as follows. Two people are equivalent if and only if they were born in the same year. That is clearly reflexive. Everybody is born in the same year as themselves. It's symmetric. If Alice is born in the same year as Bob, then Bob is born in the same year as Alice. And it's transitive. If Alice is born in the same year as Bob, and Bob is born in the same year as Charlie, then Alice and Charlie are born in the same year. So that's an equivalence relation, and it's not equality, because Alice and Bob are not the same people, but we say they are equivalent. So in this case, what are the equivalence classes? So the equivalence class of Alice is the set of all people that were born in the same year as Alice. So you can think of equivalence classes as a family or a collection of all things that are equivalent to each other. Let's do a second example with the same set. So this is a different equivalence relation on the set of all people. Let's say that two people are equivalent if and only if they have the same last name. That is also obviously reflexive, symmetric, and transitive. And now the equivalence class containing a particular person, A, is the set of all people with the same last name as that person. Now here's what I want you to notice about equivalence classes from these two examples. And the same thing is going to hold in general. That if you have the set of all people, so imagine this. So this is a set of all people. Let's do this first example, where two people are equivalent if they're born in the same year. Then, first of all, everybody is in some equivalence class. So maybe Alice is born in 1979, and maybe so is Bob, and so is Charlie. So, and then there's going to be a ton of other people born in this year as well. And then maybe someone else, maybe David, is born in 1991, and a whole bunch of other people are as well. So notice that the equivalence classes, we say partition the set, meaning they're disjoint. Nobody's going to be in two classes, but they also cover everything. Or in other words, everybody is in one of the classes. So you are never going to have a person that's not in any class. Everybody gets covered. Let's formalize that. Let R be an equivalence relation on a set big A. If B is in A's equivalence class, then A and B have the same equivalence class. And second, if B is not in A's equivalence class, then those two equivalence classes are disjoint. Together, this means that the set of equivalence classes forms a partition of the set big A. So let's motivate this with this example up here. So if Bob is one of the people born in the same year as Alice, then the set of people born in the same year as Alice and the set of people born in the same year as Bob are the same. That seems obvious. And similarly, if Bob is not one of the people born in the same year as Alice, then the set of people born in the same year as Alice and those born in the same year as Bob are disjoint. So that's one of those things where every book is going to prove this formally, and it's almost too obvious to prove, or not too obvious to prove, but obvious enough that you don't need to. But that said, it is always good practice to figure out how to mathematically establish things that seem obvious, because there's many things that are not obvious that you still have to use those same techniques. So let's do at least the first one. So we need to show that the equivalence class containing A is equal to the equivalence class containing B. So we want to show this. So we have to show two things. We have to first show that the equivalence class containing A is a subset of the equivalence class containing B, and then vice versa. I'm just going to do one of these. So for the first one, we have to take an arbitrary element x in A, and we have to show that, in the equivalence class of A, and show that it is in the equivalence class containing B. So let's do that. So let's let x be an arbitrary element in the equivalence class containing A. Then, by definition, x is equivalent to A. Now, because B is in this equivalence class as well, so since B is in this same equivalence class, we know that A is equivalent to B. So now we have x is equivalent to A, and A is equivalent to B. So by transitivity, x is equivalent to B. So by transitivity, x is equivalent to B, and that means that x is in the equivalence class containing B. So there's nothing really too hard about this, but it is a skill to use these definitions and put them in the right order and use language sensibly to reach a conclusion. So this, again, shows this containment, and I will let you pause the video and, as an exercise, try to show the other containment, that the equivalence class containing B is a subset of the equivalence class containing A. It's almost analogous, but technically not quite. And then I'll let you do the second one as well. If B is not equivalent to, if B is not in the equivalence class containing A, then the two equivalence classes are disjoint. And I'll say a hint about that. I think, once again, it's hard to prove that two sets have an empty intersection, so it's probably easier to do the contrapositive. So suppose that these two things are not disjoint, then show that this assumption fails. So in other words, for part 2, suppose that x is in the intersection of, or is in the equivalence class of A, and x is in the equivalence class of B. I.e., suppose x is equivalent to A and x is equivalent to B. Well, then what can you say? Well, I said I wouldn't do it, but now here I am. Then by transitivity, A is equivalent to B, and which means B is in the equivalence class of A. And so that establishes this second statement via the contrapositive. Let's move on to example 2. I actually did this example in the previous lecture. So we just talked about the equivalence relation, not the equivalence classes, because we had not defined those. Let's let S be the set of 8 graphs shown below. And the equivalence relation, say 2 of them are equivalent if they are isomorphic, which just means that they have the same structure. So without formally defining that, I think hopefully you agreed that these 2 graphs have the same structure, as do these 2 graphs right here. So the first 2 are the complete graph on 4 vertices with 1 edge missing. And these two graphs are the line graph on 4 vertices. And then the other 4 graphs have different structure than everything else. This one has a 4 cycle and nothing else. This one has a 3 cycle and a spoke. This one has 2 3 cycles, and this one doesn't have any cycles at all. So, there's an equivalence class. So there's 4 equivalence classes of size 1, and then there's these other 2 equivalence classes of size 2. Our next example is similar to what we did in the previous lecture. No pun intended. Let's let Mn of C be the set of n by n matrices with coefficients from the complex numbers, and the equivalence is similarity. So that means, remember that A is equivalent to B if and only if we can write A as P, B, P inverse for some invertible matrix P. In this case, the equivalence classes are the similarity classes of matrices. So the equivalence class containing a matrix A is, by definition, all matrices that you can write as P, A, P inverse, where P is an invertible n by n matrix. In our fourth example, let's let V be any finite set. If we construct any undirected graph with vertex set V, then that defines an equivalence relation, where V and W are equivalent if and only if they lie in the same connected component. So what I mean by this is, suppose we have 6 vertices, A, B, C, D, E, F. Consider the edges. Suppose we have edges like this, and suppose F is by itself. Then there are 3 equivalence classes. A, B, and C are in an equivalence class, D and E, and then F is by itself. Moreover, if we take any arbitrary partition of V, whether or not V is finite, then that defines an equivalence relation. For example, consider just a class of students. I can put students into groups, and I can just say the groups are the equivalence classes, and everyone in your own group you are equivalent with. Any partition of students into groups is going to define such an equivalence relation, and we can do that with any set. Every equivalence relation defines a partition, and conversely, every partition of a set defines an equivalence relation. Our fifth example is about bitstrings, which we can think of as length n Boolean vectors, or just length n Boolean strings, meaning we can write them as like 0, 0, 1, 0, or as 0, 0, 1, 0, 0. Either of these are fine. So given one of these things that has length n, the Hamming weight, h of x, is the number of ones in that string. For this example, I'm going to let n equal 3 and consider the equivalence on the set of length 3 Boolean vectors, or strings, where x is equivalent to y if and only if they have the same Hamming weight. This graph describes what the equivalence classes look like. 1, 1, 1 is in a class by itself. 1, 1, 0, 1, 0, 1, and 0, 1, 1 are all equivalent because they have Hamming weight 2. 1, 0, 0, 0, 1, 0, and 0, 0, 1 all have Hamming weight 1, and then 0, 0, 0 is by itself because it has Hamming weight 0. For our next example, notice that there are infinitely many possible digital logic circuits with n inputs. One reason why you can see there's infinitely many of them, because you can just keep stringing together knots, get a chain as long as you want to. However, there are only 2 to the n Boolean functions with n inputs. To see why it's exactly this number, Well, just consider the set of truth tables. Every function defines a unique truth table and vice versa. So a truth table is defined by its value at all of the inputs, and the inputs are length n binary vectors, and it's easy to see that there's going to be 2 to the n of these. So for each row in the truth table, the output is either 0 or 1. And so there are clearly 2 possibilities for each row, and there are 2 to the n rows. So that's how many Boolean functions there are. So let's declare 2 digital logic circuits to be equivalent if and only if they give the same output on all inputs. For example, this circuit on the left is not P and not Q, and this one on the right is not, parentheses, P or Q. So we know that these expressions are equivalent logically, so we will say that these digital circuits are going to be equivalent. Now there's many other ways we could define equivalence relations of circuits, but this is really the only one that actually makes the most sense. Our next example is modular arithmetic, which you're already familiar with, whether you know it or not. Here, our set is the integers, and we're going to fix some integer n bigger than 1. We say that a and b are equivalent if and only if a minus b is a multiple of n. To motivate this, let's think back to a prior lecture where we looked at the division algorithm, and there we were given an integer n and d, and we wanted to divide d into n, and we wrote that n was d times some quotient plus some remainder, and the remainder was between 0 and d, but strictly smaller than d. And there, remember, q was, we wrote it as n div d, or just n divided by d, and r was n mod d. So we use this term mod to mean the remainder when we divided d into n. So that's going to come up again, and that's why we actually use this term modular arithmetic in the name. When speaking of this equivalence relation, we usually say that a and b are equivalent modulo n, or equivalent mod n, or congruent mod n. We have 2 ways of writing this. Just right here, as we did, there's no n involved, so we have to specify what the n is. So we either write that as a equivalent to b with this equal sign with 3 bars, and then put the mod n afterwards, or for short, we could just put the n as a subscript of the equivalence symbol. As I alluded to above, this equivalence relation is sometimes called congruence modulo n instead of equivalence. Let's once again motivate that term modulo. And I want you to notice that if, or let's suppose that A is equivalent to B mod n, then what that means is they have the same remainder if we divide n into them. So this time, instead of dividing d into n, we're dividing n into a and b, and we're checking the remainder. So for example, suppose that we write a equals n times q1 plus r, and b is n times q2 plus the same r. So a and b are equivalent if they have the same remainder when we divide n into them. And to see why that's the case, let's subtract these 2 expressions. And if these r's are the same, then we get a minus b, and if and only if they're the same, a minus b equals n times q1 minus q2. And this means, so this is equivalent to saying that n divides a minus b, because n times some integer is equal to a minus b. And that's the definition up here. So that's the motivation for putting a mod n right here. Finally, I should say that a good way to think of this is like clock arithmetic. So 14 is equivalent to 2 mod 12. So think about telling time. 1400 hours is the same as 2 p.m. What are you doing? Without realizing it, you are taking the remainder modulo 12. Moreover, we can do arithmetic. So if we want to add 1 hour, we can say, well, 14 plus 1 is equivalent to 2 plus 1 mod 12. In other words, 15 is equivalent to 3 mod 12. And I claim we can also multiply. So if we multiply both sides of this equation by 2, we get that 28 is equivalent to 4 mod 12. Or we can exponentiate. We can say 14 squared is equivalent to 2 squared mod 12. I encourage you to check to see that this actually works. Okay, let's formalize this. Let a, b, and c be natural numbers and n a fixed integer greater than 1, and suppose that a is equivalent to b mod n. Then we can add c to both sides and equivalence is preserved. So a plus c is equivalent to b plus c mod n. Once again, as an analogy, think back to clock arithmetic mod 12. We can also multiply both sides by c. A times c is equivalent to b times c mod n. To see why this is true, suppose a equals n times q1 plus r, and b equals n times q2 plus r. And we multiply both sides by c, then we get ac equals n times c q1 plus c times r, and bc equals n times c q2 plus c r. So here we are dividing n into ac and bc, and our quotient is now c times q1 and c times q2, and the key thing here is notice that the remainders remain the same. Finally, you can exponentiate both sides. A to the c is equivalent to b to the c mod n. See why this is true? A equals n times q1 plus r. Suppose b equals n times q2 plus r. And imagine exponentiating both a and b. So we get a to the c equals n q1 plus r to the c, and b to the c equals n q2 plus r to the c. Now c might be huge, but imagine multiplying this out, and what we're going to get is we're going to get n times a whole bunch of terms, and then the only term that does not involve an n is going to be r to the c. And similarly down here we're going to get n times a whole bunch of terms, and then the only term that does not involve n is going to be r to the c. So in both of these cases they have the same remainder. We are dividing n into a to the c and b to the c, and we get some quotient and the same remainder. Oh, and one more thing. I should mention that I defined this for natural numbers, but really it holds for integers as well. Well, except for possibly c. So c in this one is an exponent. So that really does have to be non-negative, because we're only working with integers here, and we don't want to take like 2 and raise it to the the -3 power and get a fraction. But other than that, everything should work. When we looked at the division algorithm, when we divided, I called it D into N in the previous lecture, all that we required was D. This number here was positive, and in fact it is. And then the number on the left-hand side could be negative or positive. So technically I should be saying that A and B are integers and C is a natural number. What we basically showed above is that reducing modulo n can be done before or after doing arithmetic. In other words, A plus B mod n is equivalent to A mod n plus B mod n. And if you multiply A and B and reduce it mod n, you get the same thing as if you take A mod n times B mod n, and then I should actually probably add that you reduce that mod n, because it could be that what you get is bigger than n. And this is something you already know. Here I'm going to work with 10 instead of 12. And if you take 14 plus 28 mod 10, what is that? That is really, there's two ways to do it. One way is to say, well, that's 14 plus 28 is 42 mod 10, which is equivalent to 2 mod 10. So you can first add these together and then reduce mod 10. Or what you could have done is you could have first added them together, 4 plus 8. I should probably forgot my mod 10. Didn't leave myself enough room. And you get the same thing, although in this case, the answer is more than 10, so I have to reduce this and I get 2 mod 10. That's why I added this mod n right here. Because reducing mod n can be done before or after doing arithmetic, we say that arithmetic, in other words addition and multiplication, is well defined with respect to the equivalence relation. That's a term well defined that we are going to come back to. We're going to see it again. Let's examine it in a little more detail. I'll do that on the next slide. Once again, let n equal 12. The equivalence classes of Z mod 12 are the following. So the equivalence class containing 0, equivalence class containing 1, equivalence class containing 2, all the way up to 11. So equivalence class containing 2 is a set of multiples of 12. I could, of course, write this as the equivalence class containing 12 if I wanted to, or the equivalence class containing 48, or I could use any representative. The fact that addition and multiplication is well defined with respect to the equivalence relation means that it does not depend on the choice of representative. In other words, suppose we have two equivalence classes. I am going to use A to describe the first one and C to describe the second one. But it doesn't matter which one of these elements I use to describe the class, so suppose that you use B to describe the first and D to describe the second. Well then, when I add these two elements together, A plus C mod n, you do it by doing B plus D mod n. Well, it better be the case that we get the same answer. That is, the equivalence class containing A plus C better be the same as the one containing B plus D. And the same with multiplication. The class containing A times C better be the same as the class containing B times D. In the language of equivalence mod n, if A is equivalent to B mod n, that's what this means up here, and if C is equivalent to D mod n, that's what that means up here, then A plus C is equivalent to B plus D mod n, that's just this, and A times C is equivalent to B times D mod n, and that's just this. Let's now revisit a prior example, not when n equals 12, but when n equals 10. So a little while ago I looked at two equivalence classes. One of them I think contained 14 and one of them contained 28. Now of course the equivalence class containing 14 is just the same one as the one containing 4, and the one containing 28 is the one containing 8. And this is all mod 10. So what this is saying is that 4 plus 8 mod 10 is equivalent to, so in my choice are 4 and 8, but your choice might be 14 and 28, and it's not going to matter. That 4 plus 8 mod 10 is 14 plus 28 mod 10. These are of course both equal to 2. And then the fact that multiplication is well defined means that 4 times 8 mod 10, which is 4 times 8 is, I guess that's also 2. 32 mod 10 is 32, is equivalent to 14 times 28 mod 10, which I can't do in my head. Well, let's see, 14 squared is, what is that, 196? So twice of that is going to be, I think, 392, and that of course is 2 mod 10. Our last example is the rational numbers. Something I'm sure you're familiar with. They're fractions, but they're also decimals. And sometimes there's multiple ways to write them. So 1/2 is equal to 0.5, but it's also equal to 0.4999, etc. So what is a rational number? How do we define them? I like this quote by Kronecker, mathematician in the 1880s, said, "God created the integers. All else is the work of man." So let's figure out how to actually construct the rational numbers. We're going to do this by letting our set A be all ordered pairs, where the first entry is an integer and the second entry is a non-zero integer. So what I want to basically do is think of A comma B as being associated with the fraction A divided by B. So B cannot be 0. So I will construct what fractions actually mean. We'll define the relation on these ordered pairs by the following. A comma B is equivalent to C comma D if and only if AD equals BC. So the way to think about this is A divided by B as a fraction equals C over D if and only if you cross and multiply, AD equals BC. I claim this is a equivalence relation on this set A, but to check that we need to check that the three properties hold. First of all, that it's reflexive. That's very easy to do. A comma B is equivalent to A comma B. Why? Because A times B equals B times A. Next, we have to show that it's symmetric, which means that if AB is equivalent to CD, then CD is equivalent to AB. Now we have to be careful. It's easy to make a mistake here because usually we're thinking of relations as sets of ordered pairs, but now our elements are ordered pairs. So technically, when I say that these two things are related, I should be saying that CD, comma, AB is an R. And I mention this because I'll confess that when making these slides, I carelessly, for symmetric, wrote down, oh, AB is equivalent to BA, which doesn't even make sense because these two entries in A aren't even, the two coordinates aren't even from the same set. So that doesn't make sense at all. This is what we have to show. And why is this true? Well, if AD equals BC, well then CB equals DA. So that checks out. Finally, we need to show transitivity. That is, if AB is equivalent to CD and CD is equivalent to EF, then AB is equivalent to EF. And for this we need the cancellation law in the integers, which just means that if AB equals AC and A is non-zero, we can cancel A on both sides and get that B equals C. And though this sounds simple, there's a lot of algebraic systems where this fails. For example, if instead of the integers we were dealing with 2 by 2 matrices, we could certainly find a counterexample. You can multiply two different matrices to get the zero matrix many, many ways. Okay, let's do this. So how do we do it? We have to use the definition. If AB is equivalent to CD, then that means that AD equals BC. And if CD is equivalent to EF, that means that CF equals DE. So we're trying to show, what are we trying to show? That A times F equals, so we want to show that AF equals BE. So here we have AF equals BE. So let's multiply the two left-hand sides together and the two right-hand sides together. So we get that ADCF equals BCDE. And what do we know? Let's see, what's common to both sides? So we have a D in both sides, and we know D is non-zero because it's in the second coordinate. So we know that D is non-zero. So we get that, let's see, we get that A F times C equals B E times C. So this is almost what we want to show. If we could cancel the C's, we're golden. But we can't cancel the C's because the C might be zero. So what do? Well, there's really two cases. Case one is that C equals zero. We cannot cancel the C's. If that's the case, well then this fraction here, again, the way you should think of this is A divided A over B, and this is C over D, and this is C over D is equivalent to E over F. So if C is zero, that means that CB equals D. So let's write that down. Then AD equals CB equals 0. And what do we have? We have D not being 0, which means that A is 0. So in that case, the left-hand side is 0 anyways. Well, not here, up here. So in that case, AF is equal to 0. And similarly, I think we can show that if CD is equivalent to EF, then we can show that E is equal to 0 as well. And so A equals 0 and E equals 0. So in that case, it follows immediately that AF equals BE because those are both equal to 0. Okay, so that's the only case we had to worry about. And now the other case is when C, so case 2 is when C is not equal to 0. In that case, well, we can do what we always wanted to do, which was cancel the C's. And then by cancellation, oops, I can't spell it, C-A-N, by cancellation, AF equals BE. So in both of these cases, we get what we wanted. So that means that this equivalence relation is indeed transitive. The equivalence class containing AB, as I've already alluded to multiple times before, we can write it as a fraction. You should think of it as a fraction, A over B. And it is, by definition, the set of all ordered pairs that are equivalent to AB under this relation. So formally, that is the set of all PQ such that AB is equivalent to PQ. So you should think of this as like 1/2 is negative 1 over negative 2 equals 2/4 equals 100 over 200. So technically, you can think of fractions as equivalence classes of ordered pairs of integers. Of course, we can define addition and multiplication of equivalence classes. Well, there's many ways we can define them. I mean, let's think about how do we want to add a over b plus c over d. Well, one thing you can do is you can define this to be 0. I mean, it's silly, it doesn't make any sense, but this does work. This is well defined. What we want is, again, if 1/2 equals 3/6 and 1/3 equals 4/12, however we define it, it better be the case that 1/2 plus 1/3, that better be equal to 3/6 plus 4/12. And you know what? If we define this to always be 0, that works. They're both 0. But that doesn't make any sense. So our definition should be well defined. It should not, it would be nonsensical if our definition depended on our choice. In other words, my choice of 1/2 and 1/3 gave me a different answer or a non-equivalent answer as your choice of 3/6 and 4/12. So of course we define a over b plus c over d as the equivalence class containing AD plus BC over BD. And we can multiply two equivalence classes, A over B times C over D. And we get the equivalence class containing AC over BD. I will leave it as an exercise to check that addition and multiplication are well defined. And once again, that means that if the class containing AB is equal to the class containing CD, and if the class containing PQ is equal to the class containing RS, then if I choose to add these classes together using AB and PQ, then I get A over B plus P over Q. Remember, A over B is just shorthand notation for the equivalence class containing A comma B. And you choose to use C, D, and RS, you're complete right to do that. So C over D plus R over S, then we better get the same thing. And similarly, if I multiply the fraction A over B times P over Q, multiply these two classes, and you decide to use CD and RS, you get C over D times R over S, we better get the same thing. So I'm not going to go through all the details, it's kind of messy algebra, but let's see how it would go. So if I add A over B plus P over Q, I'm going to use this more vertical fraction notation now. Then by definition, let's see, so using this definition up here, what do I get? I get A Q plus BP over BQ. And when you add these things up, you get, what you better get is, well, let's see, you do get CS plus DR over DS. I mean, that's what C over D plus R over S is, and it better be the case that these two things are equal. Now, how do we show they're equal? Or equivalent. They're the same equivalence class. Now, what does that mean? Remember, that means, so we want to show, what it means if two fractions are the same. That means that if we do that cross multiplication, we get the same thing. So we need to show that AQ plus BP times DS, that's these two, equals this product, equals CS plus DR times BQ. So that's what we have to show. What else do we have to use? Well, this first equivalence tells us that AD equals BC. And this second one tells us that PS equals QR. So it's a bit of algebra now to use these two expressions here to show that this equality. But that's what we have to do. And then finally, right down here, I think I might go a little bit further here. This is a little bit easier. By definition, AB times PQ is AP over BQ. And what we have to do is show that that is equal to what you get when you multiply those two things, CR over DS. And of course, to show that, what we have to do is we want to show that APDS equals BQCR. So this product equals that product. And so I'll put a double star there, and all we have to work with is this up here. So that's something that I think we could probably do. And I'll leave that as an exercise for you to figure out. I think it should be pretty simple. I think if you multiply, if you multiply AD, yeah, this is easy. AD times PS, you get the left-hand side. If you multiply BC times QR, you get the right-hand side. So that's why this holds. It's just a little bit messier, but the same basic premise to show that. So this is why multiplication is well defined. We also have to finish the details to show that addition is well defined. Okay, so that's the end of the lecture on equivalence relations. And next time, we'll do partial orders. So stay with us.